Garbage collectors, or by their more proper name, automatic dynamic memory management systems, have been essential elements in why managed languages like Java have become so popular over the last couple of decades. Garbage collectors provide a huge boon to the productivity of developers, working quietly in the dark, doing the hard work of allocating space for newly created objects, freeing that memory for reuse when an object is no longer needed, defragmenting memory, and even doing other tasks like deduplicating objects, removing entire classes of problems associated with memory management from Java developers, allowing Java developers to focus on implementing business behavior. Often, the most important decision in regard to performance configuration is setting max heap size, and leaving it to the JVM and garbage collector to figure out the rest. However, for those mission critical applications that might be receiving thousands or even millions of requests per minute and dealing with gigabytes of active memory, choosing and properly configuring your garbage collector can become a critical task. And understanding how a garbage collector works is an important step towards configuring it correctly. If you're on JDK 11 or later, chances are that garbage collector is a G1 garbage first garbage collector, Java's default garbage collector, the subject of this episode of Stackwalker. If you're interested in learning more about the G1 garbage collector, other Java topics, or how to find a local Java users group, and more, be sure to check out dev.java, link in the description. G1's history goes back farther than any other topic I have yet covered on Stackwalker, with G1's roots extending all the way back to 1999. Though the story really begins to move in earnest in October 2004, when at the 2004 ISMM conference, the white paper outlining the G1 garbage collector was initially presented. The authors of the paper described a server style garbage collector targeting multiprocessor machines with access to large amounts of memory. This design goal of G1 was responding to an interesting phenomena happening in computer technology around that time. Although Moore's law was still well in effect with transistor counts doubling every 2 years, clock speeds were starting to plateau because of issues relating to heat dissipation. This led to a change in CPU design philosophy as chip manufacturers began to prioritize multi core offerings, like, for example, IBM's Power 4 and Power 5 CPUs, and multi threaded processors, like Intel's hyperthreading, which was introduced with their Xeon and Pentium 4 processors in 2002, which improved parallelization. Simultaneously, Moore's Law was rapidly bringing down the cost of memory, with per terabyte prices falling from tens of millions of dollars at the start of the 90s to hundreds of thousands by the start of the knots, to now around 10K today. The future of computing lies in parallelization and working with multi gigabyte heaps, and Java needed a garbage collector that could take advantage of those resources. At the time, the garbage collectors available to Java developers, the serial, parallel, and CMS garbage collectors, were not well suited to take advantage of these new computing resources. The serial and parallel GCs performed almost all their work during pauses. For the serial GC, utilizing only a single thread, it could only handle about a 100 megabyte heap before running into pause time issues. For the parallel GC, pause time started to become an issue around 2 gigabytes. The CMS, Concurrent Mark Sweep garbage collector, could perform more concurrently but utilizing only a single thread. This meant that with the available GCs, there would be an upper limit on the size of the heap a Java application could support before running into pause time issues, which could lead to a long term competitive disadvantage for Java if a GC option wasn't available that could work with large multi gigabyte heaps. So that's the backstory behind G1's design, and it's all well and good enough to have the goals of working with multi core processors and multi gigabyte heaps, but how is this actually accomplished? Fittingly, the documentation on G1 provides guidance here. By the G1 team's own self description of the G1 garbage collector, it is generational, incremental, parallel, most concurrent, stop the world, and evacuating garbage collector. All right, that's a lot, so let's go ahead and get started by covering generational. At a very high level, a generational garbage collector divides the heap into two conceptual generations: a young generation and an old generation. As an application runs and objects are allocated into heap space, they are initially placed into the young generation. Though note there is one big exception to this rule for G1 that we will cover later. Generational garbage collectors divide up the heap this way to take advantage of the weak generational hypothesis, which posits that most objects will survive for only a short period of time. Generational garbage collectors take advantage of this characteristic by frequently scanning the young generation for unreachable objects. This allows for more efficient use of CPU resources as more time is spent in a portion of the heap that is more quote unquote dense with unreachable objects. For objects that prove more resilient, they are eventually promoted to the old generation if they survive enough GC cycles. The old generation is less frequently scanned than the young generation, typically requiring certain conditions to be met before it's scanned, which we will cover later. Going from generational, we smoothly move into the incremental characteristic. To understand how G1 implements its incremental behavior, we need to go into more detail how G1 handles a heap. If you watch my video on the Z garbage collector, you would already be familiar with the concept of a regionalized garbage collector. However, G1's approach to regionalized memory management is somewhat different from GTC's. Whereas GTC uses a dynamic region model with a varying number of small, medium, and enormous size heap regions depending upon the number of active objects, G1 instead opts for a uniform region layout, dividing a heap out into equally sized regions. Region size can be manually configured, which as of JDK 18 can be as large as 512 megabytes. If no region size is provided, which is generally the recommended configuration, G1 will use internal heuristics to calculate the number of region and size of regions, based upon configurations like max heap size. Applying knowledge from the previous section, these regions are divided into two primary types, young and old. Note that only a subset of regions in the heap will be active at any time, which is why many are grayed out. We will also cover later why it's important to have some amount of headroom above the expected life set when setting max heap for G1. But back to incremental garbage collection. We already touched a bit on how G1 is an incremental garbage collector, in that it frequently only scans the young regions of the heap. However, G1 will occasionally perform what is called a mixed collection, where, along with their young regions, it also collects some of the old regions. We will cover in later section when G1 will reclaim old regions. However, when G1 does reclaim old regions, it doesn't choose the old regions randomly, but the regions that have the most garbage, the most unreachable objects, hence the name garbage first. Though this raises the question, how does G1 know which regions have the most garbage? To answer that question, we need to dig a bit deeper into G1's architecture. To figure out which old regions to reclaim, G1 primarily relies upon remembered sets and a write barrier. So, what are these concepts? Starting with remembered set, applications will make associations between objects, like in this simple example of a person class that includes an address field, which is also a class. It can often be a case where the references cross regional boundaries, like in this example between two old regions. When this happens, G1 will need to make a note of this interesting reference in a table. This is necessary as during a garbage collection, it's possible that only one of the regions is selected for collection. Like here, where the region containing address will be reclaimed, but the region containing person is not. Using the remembered set, G1 can use it to ensure that all cross-region references are updated so that when the application works with the person instance, it will be able to retrieve the current location of the address. It's worth noting that not all cross-regional references are considered interesting. Cross-region references between young regions would not be interesting as all young regions are included in every garbage collection. Young to old references would also not be marked as interesting, as the reference originates in a young region and so would always be included in every garbage collection. However, an old to young reference, as the old region might not be included in a garbage collection, so its reference might need to be updated. Of course, the question you might be asking is how does G1 become aware of cross region references? This is accomplished through the write barriers. Write barriers are pieces of garbage collection code that can be embedded in application code by either the hotspot interpreter or the C1 or C2 JIT compilers. Which of these processes used to add the right barrier code depends upon the level of optimization needed. Right barriers, as the name implies, are injected where application code is modifying the value of a reference. In the above code example, a right barrier would only be injected in the setAddress method as that is updating a reference, whereas setAge would not need a right barrier as age is an int, which is a primitive value. Going through the exact behavior of a right barrier is a level of detail beyond this video. At a high level, the right barrier contains logic for checking if a reference is in the same region, checking if the new value is null, checking if the region is young, and making all the necessary updates to bookkeeping, like remembered sets, to reflect the results of these checks. Using the combination of object liveness, which we will cover later, remembered sets, right barriers, and some internal heuristics, G1 is able to calculate the ideal old regions to perform garbage collection on, with one of the top priorities being regions containing the most garbage. The regions the garbage collector designates for collection is referred to as the collection set. Before moving on from the topic of how G1 divides up the heap, I need to return to the one big exception that G1 makes for when it doesn't allocate new objects into the young region. And this is for humongous objects. Objects larger than half the set region size are placed into their own separate regions tightly fitted to the nearest region size increment. So if region size is set to 16 megabytes and there is a 9 megabyte object, it would be placed into its own 16 megabyte region. And a 17 megabyte object would be placed into two consecutive 16 megabyte regions. Humongous objects are not placed into the young generation, though technically not the old generation either, as they are checked with every garbage collection like young generation regions. Next, let's explore somewhat appropriately the topics of parallel and mostly concurrent together. Or is it in parallel? Or is it concurrently? Anyways, parallel and concurrency are not synonyms in GC parlance, but refer to distinct qualities. I covered this topic in a bit more depth in my ZGC video, but to briefly cover it again, parallel is simply the quality of the garbage collector being able to utilize multiple threads for performing garbage collection work. The actual design implications of this ability show up in many areas with error checking, bookkeeping, and post action checking and cleanup to ensure consistency. Such is the cost of coordinating between multiple actors. Concurrency, on the other hand, is a characteristic of garbage collectors being able to perform work while the application, or as it often is called in garbage collector lingo, the mutator, is working. Like with parallelization, concurrency also comes with a number of architectural trade offs to ensure the garbage collector doesn't cause errors in the application while performing its work. A concurrent garbage collector can also utilize multiple threads in parallel during its concurrent cycle. It's not a given a concurrent garbage collector can do this. As mentioned earlier, one of the reasons G1 replaced CMS is that CMS can only use a single thread concurrently. Concurrency doesn't come for free, however, and there are advantages and drawbacks to concurrency. The primary advantage to concurrency is reduced pause time, as work that would normally be done during pause time can be performed while the application is running. This has a second order effect of being able to work with larger heaps. The drawbacks is that performing this work concurrently means garbage collector is taking up CPU resources that the application could be using, leading to reduced throughput. Additionally, concurrency increases architectural complexity to the garbage collector, which can lead to increased memory and CPU overhead from the additional bookkeeping and checking necessary to maintain system integrity. While G1 and GDC are both concurrent garbage collectors, what they actually do during their concurrent cycles is very different. GGC attempts to do virtually everything concurrently, while G1 only does certain activities and its concurrent phase isn't always running. At a high level, G1's GC cycle is broken into two phases: young only, where, as the name implies, garbage collections only reclaim young regions, and the space reclamation phase, where G1 performs mixed collections, which reclaims both old and young regions. The selection of these regions we covered in the previous section. During the young only phase, G1 will regularly perform garbage collections, reclaiming young regions and promoting objects to the old region as they qualify. At a certain point, based on the internal heuristics of when old regions have exceeded a threshold for how much space they are occupying, the concurrent cycle will start. The purpose of the concurrent mark cycle is to prepare the heap for reclaiming old regions during the space reclamation phase. The concurrent mark cycle can be broken down into three high level parts. The first is the concurrent mark process, which starts with the subsequent young only pause following the old generation occupancy threshold. The concurrent mark phase process scans old regions for which objects are still currently live, one of the key factors in determining which old regions will be collected, which we covered earlier. The concurrent mark phase can span several normal young only garbage collections. Once a concurrent mark phase has been completed, there is a remark pause, which is a separate pause from the young only pauses, and no young regions are collected during this pause. Instead, during this pause, G1 finalizes the marking process, performs class unloading, reclaims completely empty regions, and performs a few other duties. Following the start of the remark pause is the concurrent rebuild remembered sets and scrub regions phase. Yeah, that's a bit of a mouthful. During this phase, G1 will be used to reclaim free space in the selected old generation regions. At the end of the concurrent rebuild remembered sets and scrub regions phase is a cleanup pause. Like the remark pause, this is not a young only pause, and no young regions are collected. During this pause, the results from the concurrent rebuild remembered sets and scrub regions phase are finalized, and a determination is made if a space reclamation phase will follow. If a space reclamation phase is needed, the cleanup pause is followed by the prepared mix pause, which is used to prepare the garbage collector for work during the space reclamation phase so that it can maintain pause goals. During the prepared mix pause, it is calculated the minimum number of regions that must be collected during mix pauses during the space reclamation phase. G1 will then enter the space reclamation phase. Pauses during this phase are mixed collections where, along with young regions, old regions are also collected based upon the work done during the concurrent phase. G1 will leave space reclamation phase when it determines performing more mixed collections is no longer worth the effort. This is only a high level overview of the concurrent phase. Thomas Schassel, the lead engineer of G1 GC, provides a more detailed breakdown of the G1 concurrent phase, and I would suggest checking it out, his blog article on the subject on screen and in the description, if you would like more detailed information on what exactly happens during the concurrent phase. Finally, the last two terms, stop the world and evacuating, we will also cover together. In the previous section, we covered G1 GC cycle. Each of those dots on the circle represent a pause. A GC pause is a period where the GC stops the mutator, the application, while it performs its work. During this time, all work in the application is halted. The GC pausing the application while performing its work comes with the obvious advantage of simplifying the architecture and behavior of the GC, as it doesn't have to worry about accidentally moving a reference the application was actively using. This is balanced by the equally obvious downside, as this can increase latency, as any request must wait until the GC pause completes before the application can continue processing the request. There are a number of options for tuning pause times in G1, a topic we'll cover a bit later. Finally, let's cover evacuating. Garbage collection is a bit of a misnomer, as it implies during a GC pause, G1 is looking for objects that are unreachable and removes them. In reality, for an evacuating garbage collector like G1, G1 is instead looking for the still reachable objects and preserving them. This happens through a process of evacuating still reachable objects to a new region. Though no object actually moves, it is instead copied into the new region. Before we get to that, it's also worth noting there are actually two types of young regions: Eden and Survivor. Survivor regions are marked with an S. Newly allocated objects are placed into an Eden region by the garbage collector. Living objects in an Eden region will be evacuated to a Survivor region. Any still reachable objects in a Survivor region that are not yet eligible to be promoted to an old region are also evacuated into Survivor regions. Any objects in Survivor regions that are eligible for promotion to an old region are promoted, moved to a newly created old region. The evacuated objects are then marked as eligible for reclaiming, though G1 doesn't actually delete the objects in those regions, just those regions are eligible to be used again. The evacuation process is also why it's important to provide max heap overhead beyond the expected size of the live set, because if G1 isn't able to find enough empty regions to evacuate objects into, it will either have to go into more costly processes like compacting regions and evacuating objects into active regions, or performing more frequent pauses in an effort to reclaim space, all leading to undesirable performance characteristics. The general recommendation is to provide an overhead of 25%. So if you're expecting your live set to be 4 gigabytes, you will want to set max heap size to 5 gigabytes. One final note on the topic of evacuation: humongous regions aren't generally eligible for evacuation as they consist of a single object which will remain in place until the object is no longer active and the humongous region reclaimed. The only exception to this was recently added in JDK 21. Starting in JDK 21, G1 will make a last ditch effort to avoid out of memory exceptions by moving humongous objects to free up memory. Since JDK 9, G1 has been the default GC of the Hotspot JVM. G1 GC was chosen for the default as its performance characteristics cover a wide variety of use cases. Still, before choosing to use G1 GC, it's worth considering if G1 is the right choice for your use case. As part of the reason multiple GCs are available is each of them have their own ideal use case. If you're working with a small heap, 100 megabytes or less, or have access to minimal system resources, the serial GC would likely be your best option. If maximizing throughput is a priority, even at the cost of longer pause times, parallel GC will likely be the best choice. As we covered in the intro, G1 GC was designed for large heaps, heaps greater than 2 gigabytes in size. G1 provides shorter pause times through its concurrent phase, as we covered in this episode. However, as G1 doesn't overly depend upon concurrency, it still provides high throughput, though not as high as parallel. Finally, if you are working with extremely large heaps and or need to keep latency at a minimum, G1 might be the best option. Choosing the right GC for your use case can help significantly in getting an application to meet your performance requirements. If G1 does match your use case, but you're still running into performance issues, G1 has many performance tuning options. If improving throughput is the primary concern, increasing GC max pause times with a default of 200 milliseconds and G1 max new size percent values can help. Of course, manipulating this value lower can also be used for reducing pause times. On the subject of pause times, setting max and minimum heap size to the equal values can help, as well as enabling always pre-touch, as it moves the process of preparing the heap to during the VM startup. If your application is pausing too often, modifying the values of GC pause interval mills and max GC pause mills so that the former is meaningfully larger than the latter can help. Finally, if you're working with a lot of huge objects and are having issues with memory fragmentation, modifying G1 heap region size can help. Setting G1 heap region size so that it closely matches the size of huge objects would be the goal here. Though this is just a high level overview of tuning G1, the Hotspot GC team maintains an entire section on tuning G1, which covers this topic in more depth than I can here. Be sure to check it out on the Hotspot Virtual Machine Garbage Collection Tuning Guide, link on screen and in the description. Finally, let's take a brief look into the future of G1. The biggest change on the horizon for G1 is the implementation of region pinning defined in JEP 423. Region pinning would improve G1 interoperability when working with JNI by allowing arbitrary regions to be pinned to a specific location so that objects in those regions can be accessed directly without fear of being moved and without slowing down GC activity. Considerable groundwork has already been done to G1 to prepare for this change, which can be seen in Thomas Sassel's blog. Again, link in the description, so be sure to check that out, as well as the JEP for this change. A more speculative change to G1 might be changes to its barriers. A June 2023 master's thesis by Yevgenis Protopovofis, apologies for any mispronunciation, investigated the possibility of G1 switching to a throughput barrier and provides an interesting analysis of G1, definitely worth a read. Again, link in the description. G1 is a fascinating piece of technology. It was originally conceived at a time when computers with multiple gigabytes of memory were relatively rare, and multi core, multi threaded processors were novel concepts. Yet, despite the considerable advances in computer technology over the 20 years of G1's existence, it has been able to keep pace with that change, and as a result, help keep Java as a top choice for organizations requiring applications to work at massive scale. Well, that's it for this episode of Stackwalker. Until next time, have a good one.